Hi everybody, welcome back to class. We've just got a couple moments until 11:30, but thanks for arriving on time and early, and we'll just be ready to go in a minute. Hey there everybody. Kalaya, Leo, Maya, Jamie, good to see you guys. Good morning. Hey everybody. Alicia, John Red, Samir, hi Karina. Hello everybody. Okay, guys, well, welcome back. I'm going to go ahead and let us get started. So thank you all for being here. First of all, did anybody notice my message from today, this morning, just with the new homework distribution? Due in 2 weeks? Let me know if you got it. I want to make sure that, okay, thanks. Good, Lily. So some of you maybe haven't had a chance yet to look in your inbox or whatever, but no big deal. I just sent this morning the next homework assignment. It's due in 2 weeks. Karina, if you haven't looked, you'll find it if you just go to either your school email or to our Titanium page for this course. But it's the newest announcement just delivered this morning. And yeah, it's just a homework problem set. This new homework problem set basically deals with translations and truth tables. So truth tables are added to this homework problem set, as opposed to in homework problem set 2, it was just translations. So you got 2 weeks to work on that. I'm finalizing the grades on the midterms. I'll let you guys know over the weekend when they're ready. They should be ready relatively soon, certainly within, my normal policy is to try and always make sure things are completely graded within a 2-week span from when they were done. So no later than Wednesday of next week, but I'm thinking much sooner than that. This weekend is what I'm targeting on that. So whenever the grades are in, any individual student could simply check with me to get their score on that. Okay, so today we have an important meeting because we're moving on to a new topic in this class. We still have one major thing to do in logic, and in a way, it's kind of almost the most important and fundamental thing in logic that we need to learn, which is how to do proofs, how to do what are called derivations. And so that takes us now to our chapter 5 of the book, which is all about derivations. Okay, derivations. So now, let me, as before, I'm going to pull up a quick Zoom meeting here so that we can share screen. And then we'll be able to look at some of the information in the book as I talk to you guys about how to do these derivations. But before I do show that, I don't want to jump in too quickly. I want to first start by just talking about the concept of what a derivation is. So when you have an argument in everyday life, we all have learned that there's a conclusion, and this conclusion is based on the premises given in the argument. So something along the lines of, if John runs, then John will sweat. John did go running, therefore John has sweated, right? When we reason in everyday life naturally, like we draw conclusions from another set of facts. So far in this class, all we've talked about are what arguments are, what the logical properties of arguments are, whether the propositions in the argument are logically true, logically false, indeterminate, whether the sentences are consistent with each other. We've learned how to translate from English into logic. We've learned how to do truth tables, but we haven't yet done anything which approaches the characteristic of natural reasoning, where somebody says, well, if this is true, then that must be true, and if that is true, then something else must be true, and therefore I reach a conclusion. So now we're going to start learning how to do derivations using the derivation rules in our logical language, SD. Now there's a set of different derivation rules for each connective that exists in logic. And as you guys know, there are 5 connectives that we've learned. There's the AND symbol for conjunction. There's the OR symbol for disjunction. There's if-then, which is the arrow or the horseshoe. There's biconditional, which is the double arrow or the triple bar. And then there's negation, which is just the tilde sign. For each of the 5 logical connectives, there are 2 derivation rules. There's what's called an introduction rule and an elimination rule. So we're going to have to learn all of these rules of derivation one at a time, and we'll take it slowly so that we make sure that you're able to digest all the information. All right, now what I will do now is put up this Zoom meeting so that we can look at the same information as one. So go ahead and check on that, and I'll start the meeting. Okay, I see you guys here. Really quick, I'm going to go and close a window over here because there's a little bit of noise pollution coming from that. I'll be right back. Sorry, Peachy. Let's go. Okay, thanks again, everybody. All right, so here we go. Sharing the screen and pulling up the chat here. Can anybody type in this Zoom chat, letting me know that you can hear me and that everything's easy to see? Okay, good. So, just gotta find my text. Yes, it's here. Okay. So let's consider, for example, the argument that's written here on this part of the textbook. If Marshall, so I guess this is like a hypothetical election or something. If Marshall survives the current scandal, and if her opponent does not outspend her, then Marshall will be reelected. If it continues to be politics as usual, Marshall will survive the latest scandal. The scandal is no longer front page news, so it is going to be politics as usual. Marshall's opponent will not outspend her, so Marshall will be reelected. Okay, now this whole passage, this paragraph, contains an argument. The conclusion of the argument is that Marshall will be reelected. And the premises given in the argument is all this information stated here before. Now, question, can we restate this argument in logical symbolism and through a series of inferences derive this conclusion from the premises that are given? So let me skip ahead a little bit. Next, they show you how you could break the premises and the conclusion out of the original passage and state them in this logical paraphrase, where the conclusion, Marshall will be reelected, is here on the bottom beneath the horizontal line, signifying that it's the conclusion. And each premise is now given on an individual ledger line above in a list. Now, the way that the argument will look is that the 4 premises listed here, the 4 premises listed here are called assumptions. When we further structure the argument into its logical form, we number the premises 1, 2, 3, and 4. So you see the numbers here to the left. And we write the word assumption to the right to designate that those were premises provided in the original argument itself. The question is, how can we get from these 4 assumptions to this conclusion below? Now, they show you a couple steps here, but I want to kind of not look at the English version of it and instead consider this logical paraphrase. So right now, let's go back up to the English sentence and see how it compares with the logical paraphrase written here below. So the first premise, if Marshall survives the current scandal and it is not the case that Marshall's opponent outspends Marshall, then Marshall will be reelected. So for that, we have this statement here. If both Marshall survives, which is letter S, and not the case that O, where O is going to stand for Marshall's opponent outspends, then in that case, so if then, the arrow, or as we can also use the horseshoe, in that case R, for Marshall will be reelected. So that's the first assumption of the argument. And we could write the full word assumption, but a lot of times logicians will abbreviate it to ASS. It looks like the word ass, but you all understand that when I write this word here, it's shorthand for assumption. Okay, so that's the first assumption. That if he survives the scandal and not outspent, then in that case, Marshall's reelected. Second premise, if it continues to be politics as usual, then Marshall will survive the current scandal. So continues to be politics as usual, they're using the letter C, I guess, for continues. So if C, then in that case, the consequent would be that he'll survive, which we already have designated as S. So that's the second premise, or we could call second assumption. Okay, third. The third premise is that it is not the case that the scandal is still front page news and it continues to be politics as usual. So it is not the case that F, where F stands for its front page news, and it continues to be politics as usual, C. Okay, that's another of the four assumptions right here. So we move on to the fourth and final assumption in the original argument, which says it's not the case that Marshall's opponent outspends Marshall. Not the case that Marshall's opponent outspends Marshall, so simply that's not the case that O. Okay, so now, let me do this. Numbering them as seen here. Okay, now what we do is we create a little line that breaks the divider between the assumptions and then the inferences that are after that. The conclusion of the argument, as you can see above, is that Marshall will be reelected right here. Marshall will be reelected. And that sentence is designated by the letter R for a reelected. So here we go. Let's derive R. That's the goal, that's the problem for you to solve, deriving R from these sentences here. So how can we get to R? Let's see it informally. Well, here, let's take it step by step. So what I'm drawing your attention to in this window is statement number 5, okay? These four assumptions are just given, but number 5 is derived. So the fifth step, we number it. We continue this vertical line down with each new added step in the derivation. And the next thing that was mentioned here is letter C. C comes from 3. How does C come from 3? Well, what does proposition 3 say? Proposition 3 says that not F and C. Well, from that fact that both not F and C, the individual conjunct follows, namely just C by itself, okay? The next step of the argument establishes S from 2 and 5. Okay? S comes from step number 2 and 5 combined. Because what number 2 says is that if C, then S. And 5, which we've just now established from 3, tells us that C is true. So if C is true, and if C, then S follows, right? Like, if one thing, then another, and we've established that the antecedent is true, so the consequent follows, therefore S. Now, the 7th step in the proof. That takes us to this proposition here, S and not O. And that comes from a combination of these two lines, from number 6 and from 4. Those two appear individually on lines 6 and 4. So since they're in the proof, we can combine them into one conjunction on line 7. And then we just have 2 more steps. Step 8 is establishing R from 1 and 7. Actually, there's only 1 more step. My bad, I didn't mean to add 2. The 8th and final step is just R. And what that comes from is number 7 and 1. Because if you examine number 1, it's a conditional. The antecedent of the conditional is S and not O, which we built in proposition 7 by conjoining S with tilde O here. Since this says if S and not O, then R, and number 7 says S and not O, that allows us to establish the consequent, which is R. And that means we're done. We've proven what we needed to prove. We've derived the required proposition from the 4 initial assumptions and then some additional inferences. Now, the one thing that's a little ambiguous to you right now is, what are these inference rules where it says from 3, from 2 and 5, from 2 and 5, from 6 and 4, from 7 and 1? Now it's our job to learn about these inference rules so that we can construct proofs like this in a systematic fashion. Okay, so I'm going to start teaching you about the different rules of inference, the different derivation rules. Let me come back to reiteration in a moment, because I think it's easier to start with the conjunction rules, okay? So here are these 2 rules that I want us to learn: conjunction elimination and conjunction introduction, all right? So we're going to learn the rules of inference 1 at a time. There's 11 total, and so right now we're going to learn 2 of the 11, right? Now, here's how conjunction introduction works. Conjunction introduction, which is known as, so the symbolism that you'll use whenever you apply this rule is conjunction symbol with the letter I. So for us, we've used this quite often, but you can also, of course, use the ampersand. Okay. So in parentheses here to the right, I'm just showing you the symbol that is used to stand for the long words conjunction introduction. It's just caret I or ampersand I. Now, here's how the rule is applied. Suppose that within a proof, you have these 2 sentences that occur on previous lines of the proof. You have P and you have Q. What conjunction introduction allows you to do is to simply combine those 2 things into one proposition, namely P and Q. So that's the schematic form of conjunction introduction, and you see that here in the window that's displayed on the shared screen. So from any 2 propositions, P and Q, we can combine them into one conjunction. So for example, like, let me talk to you about this from like everyday life. Trump is the president of the United States, and the planet Earth is the 3rd planet from the sun. Okay, so like I'm saying these 2 things separately. Number 1 statement, Trump is the president. Separate statement, Earth is the 3rd planet from the sun. Based on those 2 individual statements, I can create the conjunction that says what? Just tell me, just in English, in the chat if you can. Or on the mic, it doesn't matter. But just give me the answer. I've said one fact, Trump is president. Another fact, the Earth is the 3rd planet from the sun. And so conjunction introduction allows me to do what? Having provided these 2 individual sentences, I can then what? I can combine them, correct, Lily, into the one conjunction that says both Trump is president and Earth is the 3rd planet from the sun. That's all that this symbolism is telling you. That from any 2 individual facts, the conjunction of the 2 facts can then be formed, right? So like, I'm a professor, Dr. Vulich teaches philosophy, and the Los Angeles Lakers are the NBA champions in 2020. Those are 2 individual different points, but they can be combined into one conjunction which says and. Namely, Dr. Vulich teaches philosophy and the Lakers won the title in 2020. Okay, so we can basically build conjunctions from individual components. know this also, that the letter P and Q here are what we call meta variables. So it does not have to be an atomic sentence letter that is used to combine two things in a conjunction introduction. You can combine two sentences of indefinite complexity. So it could be that you have a conditional, and then you have a disjunction, and then you could combine the two things into like a big conjunction where on the left half of it you have a parenthetical formula, and flanking it on the right you have another complex formula that are combined. So any two sentences, whether it's a sentence letter or whether it's a complex formula, can be added together on a subsequent line by using conjunction introduction. All right? Let me show you how this would look in an actual proof. So suppose this is your elementary proof that you've been given. So you've given two assumptions, and one of them is A, one of them is B. These are just assumptions. They're premises that are provided to you. And suppose that the problem says derive the formula A and B. Well, let me get the right symbolism. Okay, so to do that, the way of solving the problem is to do inferences until you get this formula on one of the lines of the proof. This one will be very easy. On line 3, we simply write down A and B. And now over here to the right, this is what's called the justification column of the proof. Because these two statements were provided to you as assumptions, the justification for them is ASS, assumption. But because we are the ones who have now added this statement to the proof, we have to justify it by citing the relevant rule of inference and the numbers of lines which we are using the rule on. So what will we write in the justification column here? What rule allowed us to put this on the proof? It's the rule we're learning. And so you could just tell me its name again. The rule that generated this sentence is conjunction introduction. And what are the numbers of the two lines where we have taken the elements to form this statement? So we also have to give that. We have to give the name of the rule, and then we have to give the line numbers. So what are the numbers that are used to form the third sentence here? It's 1 and 2, correct. So conjunction introduction on premise on line 1 and 2 gives us this full conjunction, and that's it. There you go. That's the proof. Derive A and B. If you've been given those two propositions, it's pretty straightforward. Let me give you another look at this. So suppose that we have a problem, and it gives you these. A, B, and C are the assumptions. But now, the problem, the derivation to give is this formula, A and B and C. Okay, so the next line is the fourth line. With each new line, we're trying to get to the result that you're told to derive. So you're done with this, you've completed the problem when you arrive at this required statement. So what should be the inference on the fourth line of this proof? What will give us something that gets us closer to that? Tell me what inference rule, what proposition, and what numbers I'll cite. So what do you think I should build on line 4? So far we only have one inference rule, so there's really not too many options. Lily, you say A and B. So we have to now say where that comes from in the justification column. Good, that is conjunction introduction on lines 1 and 2. But we're not all the way done yet, you see, because this is what we have to derive, and we don't have it yet in the derivation. So we continue to another subsequent line of the proof, line 5. What can be done on line 5? Anybody can tell me that. We're really right there at the doorstep of finishing this proof. But we have one more step to do. So it's line 5. Line 5, Samir, okay. Let's ask this way. What's the statement? What's the sentence that will be written here in line 5? It'll say A and B and C, right, Lily? That's the correct bracketing. A and B and C. Where is that coming from? What is the justification for this, for line 5? Just need the rule name and the numbers involved. Okay, it's conjunction introduction 3 and 4. Perfect. That's the proof. So what this shows you is basically this. From these 3 statements, which are given as premises, this conclusion can be derived. In other words, it's a valid argument that takes us from these 3 premises to this conclusion. And we show that by a series of inferences, which takes us from the premises to the conclusion. So from any 3 facts, A, B, and C, it does logically follow that the conjunction of the 3 facts is the case. This one, the only difference between it and the previous example was that I wanted you to see how you could combine line 4, a whole conjunction, with an atomic sentence on line 3 to get to the required result here. Okay, so we're learning one of the derivation rules so far, conjunction introduction. Let's move to the next one. Next, I'm going to teach you conjunction elimination. Okay. And this is symbolized by conjunction E, or if you prefer, ampersand E. The conjunction elimination rule. Now here's how this one goes. Suppose that you have a conjunction of this form, P and Q. Conjunction elimination allows you to do this, to remove one of the conjuncts from either the left or right. So suppose that you want to break this down and just get P. That's what conjunction elimination provides, allows. Another possible option is the other way. Say you have P and Q. Conjunction elimination allows you to thus say Q. All right? Now let me talk to you about the real-world logical significance of this. From a conjunction of 2 facts, the individual conjuncts in the conjunction necessarily follow. Okay, so like for example, I'm a professor, so I'll say it in the third person. Dr. Vulic is a professor of philosophy. And Joe Biden is the Democratic nominee for president. That's a conjunction. So both Dr. Vulic teaches philosophy and also Biden is the Democratic nominee. Now, from that conjunction, we can say that one thing that is true, if the conjunction is true, is that what? If it's both true that I'm a professor and that Biden is the Democratic candidate, then from the conjunction of 2 facts, one thing that follows from them is, for example, the individual statement that what? That Biden is a Democratic candidate, or that I'm a professor of philosophy. If this sounds to be too much of a high-level example, I don't know. Suppose I have an apple and a banana in my lunch bag, like both of them are there. So both I have an apple and I have a banana. What is something that follows from the fact that I have both of those things? Anybody can tell me. If I do have an apple and a banana, then clearly, by implication, I do have simply a what? You follow me? That I have an apple, yes. So if I have both, then I of course have one. There's no way to say I have both, but I don't have one of them, okay? So from a conjunction of both, the individual conjuncts, of course, follow. And that's all that says. So whenever we know some conjunction is a fact, we can thus infer that the 2 parts of the conjunction are facts. You know, so like I was born in March, and I'm wearing a t-shirt, so of course I'm wearing a t-shirt is one thing that comes from that. Or I was born in March is a fact that follows from that. Okay, so that's conjunction elimination. Let's see how it will work in like an actual example. Suppose we had a problem like this. So the assumption is just A and B. And the problem says derive A. So what's to be written on line 2? You have to say in each new line what sentence that you're adding to the proof, and then you have to provide the logical justification for it to the right. So here's your goal to get to A, and what you've been given is A and B. So how do you get to A? Just using our new rule. We will write under line 2 what? Yes, Leonard? We write the letter A. And over here to the justification column, we have to cite the rule name and the number. So it is conjunction elimination on line 1, exactly. Now, with conjunction elimination, how many lines do you cite whenever you use the rule? 1 line, because it's from the line where a conjunction is, and you're stripping off 1/2 of it. And that's how conjunction elimination works. With conjunction introduction, how many line numbers do you have to provide in the justification column? When it's the introduction rule, you have to give the number of how many lines? 2, exactly, Lily, because to build a conjunction, you have to have 2 components that are put together. To disassemble a conjunction, there's just 1 conjunction on a line, and you're removing one of its conjuncts. Okay, so just get in the habit of knowing that. When you use conjunction elimination, there's only 1 line to cite. When you use conjunction introduction, there's always exactly 2 lines to cite. I'm just trying to get that in your mind right away because it's the source of some easy mistakes that people will sometimes make later, confusing themselves, thinking, how many numbers do I write down though? I forget. Was it 1? Was it 2? Anyway, with conjunction rules, there's a straightforward answer. Every single case of conjunction elimination cites 1 line. Every single case of conjunction introduction cites 2 lines. Okay. So derive A, and we were able to do it. We also could have done this problem in the way of deriving B, and we would have had the same justification, but just a different sentence here. Okay. Let's try another one. Suppose that the problem provides you with this. A and B and C is the one assumption. Suppose it tells you to derive B. Okay? Walk me through the steps. What will be the next step? It's going to take more than 1 this time. In step 2 of this proof, what will take us closer to our goal of B? What will take us a little closer to that goal, B? Let me know. You have this to work with, and you have 2 rules to use, but really only one of them is going to be used here. So, on the second line of the proof, what could be given? Okay, Lily, A and B. That's good. Notice that I don't have to continue to use the parentheses once there's no further expression on the right to disambiguate what part of this is the conjunct. But anyway, A and B, conjunction elimination, line 1. Good. Line 1 is a big conjunction, and the left conjunct of it is itself a conjunction, and the right conjunct is an atomic sentence. So we're able to strip off this whole left half of the big conjunction. Since this is the main connective, we can take the one side of it off, and then we get A and B by itself on line 2. But that's not the goal, right? The goal is to get B. So we're almost there, but we need to take another step to do it. Hey, Peachy. So what do you think? What's line 3 all about? What can I put on line 3? And what justification? Let me know. Line 3. All right, here we go. Okay, Nathaniel, B, and the rule is conjunction elimination on line 2. Good, that's it. There you go. So I just wanted to show you how sometimes you have to apply the rule consecutively if there's like a nested conjunction within a bigger conjunction. So we had to basically just use it twice. Once to get A and B by itself, and then again to remove B from the right side of that conjunction. Okay. Now, let's try and combine 2 of these problems together. Or some people working on the pipes, I guess, in the apartment complex, whatever. Okay, so suppose that here's what you have to derive. Derive A and C. See that right there? Suppose you have to get that conjunction, and this is your assumption to start off with. So what do you think should be the next step of this proof? We're trying to get to A and C, and that's our big formula. So take me towards the solution. Next step. Next step on line 2. Let's see it. You only have 2 rules to use, so you've got to think about using one or the other of them. You've got conjunction introduction and conjunction elimination. And this big conjunction is all you have to work with for now. Eventually, you want to get to A and C. So just help me. What's next? Nathaniel. So second line, A and C, conjunction elimination of 1. No, you can't do that. No, you cannot do that because line 1 doesn't have A and C as one of the 2 conjuncts. So if you eliminate this main connective here, you're not going to get A and C. You're going to get either A and B on the left, or you're going to get just C on the right. So that actually wouldn't be correct. Okay, Lily, A and B. And that's based on conjunction elimination on line 1. Can we all see where this comes from? This A and B is just being taken out of the conjunction of line 1. Because A and B is the sentence that's on the left of this connective. So by breaking this, eliminating this conjunction, we get to that sentence there. Okay, but we have more work to do, because remember, the goal is A and C. So next up, Lily, on line 3, let's write C. And that's also formed on the basis of conjunction elimination, line 1. Are we all clear on where the third line comes from, everybody? Anybody's free to ask me a question anytime if you need to, if there's something that's not clear that you want me to go back over. But let's just focus on this point here. Where does this come from? It's just the right side of this conjunction up here. So in 2 steps, we had to disassemble it to get the left component separated from it and the right component separated from it. Now, instead of A and B and C all on one big line, we have them on 2 separate lines. A and B is on line 2, C is on line 3. And yet, our ultimate goal is still outside of our reach. We don't have it yet. Will we be able to go straight to A and C for step 3? No, you can't do that, no. Because when you combine A and C, you have to only have A and only have C on separate lines so that they can be combined. The justification for combining those 2 things has to have 2 numbers, but there's no 2 lines that you can number where letter C appears by itself and letter A appears by itself. C is on line 3. If we had A by itself, then yes, we could put them together, as you say, Isaiah, to form the expression we're looking for. But before we do that, we'd have to get A by itself. So there's a little bit more work to still do. Leo, good. Line 4 shall say A, and that is by eliminating this conjunction on line 2. And now, at the 5th step of this problem, of this proof, what can we do? Well, Frida, I see that you detached B, but that's actually not necessary, although it wouldn't be a problem if you did it. Unnecessary steps are not invalid inferences, but it just doesn't advance us closer to the goal, so it wouldn't need to be used, but it's a valid inference. Yes, B does follow from conjunction elimination on 2, but Leo, you're right. At this 5th and final stage, we can simply combine lines 3 and 4 together to form the desired result, A and C. That's conjunction introduction, line 3 and line 4. And then in 5 steps, we've taken it from the assumption provided to the derived result here. Does it matter what order we find C or A, John Red? Like, meaning, does A have to be above C or something? No, once you have these 2 components, C, A, we can combine them in any order. So on line 5, we could have put together C and A. And that would have also been a valid inference. But there would have been no reason to do that because the proof asks you to build this order, A and C. Does that answer your question, Dron Rep? So, like, yes, it's possible to introduce the 2 conjuncts in either order, left or right. but you want to order them in the way that gets you to the solution of the problem you're working on. So in this case, you'd want to combine them with A on the left and C on the right. But the material that you're taking them from line 3 and 4 do not have to occur in any particular order. These could be combined in the order CA, in the order AC, okay? So good question. All right, so we've learned conjunction introduction, conjunction elimination. Next, I'm going to talk to you guys about what is called conditional elimination. Okay, conditional elimination. And conditional elimination is symbolized by arrow E, or horseshoe elimination E. Okay? So when it comes to conditionals, here's how the conditional elimination rule works. Suppose that in a proof you have if P, then Q. And we're seeing the schema in the text right here. Conditional elimination. So if you have if P, then Q, and then at a future point within the proof, or anywhere else in the proof, you have the letter P, that allows you to infer Q. So that's how conditional elimination works. Let me explain to you the everyday logic and common sense behind this. Suppose I tell you that if I get shot, then I will bleed. That's a conditional. The antecedent is me getting shot. The consequent is me bleeding. So suppose if I get shot, then I bleed. But it turns out that actually I did get shot. Well, put those two things together. We said that if I get shot, then I'll bleed. By the way, now I've gotten shot. So from there, the bleeding is going to happen. You see, so the consequent, the right-hand thing that's on the tail of the arrow, is what follows from these two statements, that if this, then the consequence, and also, yes, the antecedent has occurred. So if it rains, then my car will get wet. It did rain, and so therefore my car got wet. If everybody votes, then Trump will lose. Everybody voted and Trump lost. You know, so those are examples. Does this make some common sense to you? An if-then statement says something. The information that it says is that if this event occurs, or if it becomes true, then this other thing will also be true as a result, or as a consequence of that. So if we know that the if-then is true, and we've also established that the if part has occurred or is true, then the consequent part follows after that. Okay? So now, suppose that you had a basic problem like this. Premise 1, assumption 1, if A, then B. Premise 2 says just A. Suppose you're told to derive B. This one's real easy. This is softball. What does the triangle mean? Good question, Evelyn. It just means that this is a statement that can be derived from these statements above. So it just means like here is the consequence, the result of applying this inference rule. Using the inference rule, when we have two statements like this, spits this out as a result. So like this is the output. The triangle says here's the output from these two inputs. Okay? The rule works by taking some information as an input and then providing a new statement as output. This is the statement that is the result, the byproduct of having these two earlier statements above. We can infer this from that. Okay. So here we go. What can I write on line 3? So you have to give the sentence that you're inferring, the derivation rule, and then for conditional elimination, you need to cite 2 lines. You have to cite the line where the conditional is that you're eliminating, and then you have to cite the line where the antecedent occurs that you're using to eliminate it and get to the consequent. So, question for you. Derive B from these 2 premises. What's the 3rd step? And what's the justification? Okay, Leo, B is the third step, yes. And it follows from conditional elimination, line 1 and 2. Exactly. Line 1 says if A, then B. Line 2 says A. So from these two facts, just as we see here in the general format, when you have any two facts like that, a conditional and then just the left part of it that matches the left part here later, that gives us the consequent. And we have to then just say, sorry, conditional elimination, line 1 and 2. Okay? Conditional elimination. Make sure to include the E to stand for the word elimination. Just a typo at first before I put that in there and corrected it. That's how that one would work. Okay, so let's see. What if I want you to derive this one for me in this problem? Derive A and B. Derive A and B from these. Okay. So how are we going to get that? Tell me line 3, what's the next step? Just takes a series of steps. With these derivations, practice is everything. You got to really keep trying more and more problems, getting more experience doing them. There's nothing else exactly like it. It's kind of a little like math. It's kind of a little like natural reasoning using English. But the better and better you do it, the more and more you do it. So what do you think? Next step. Don't look for the immediate solution sometimes. Just think about how you can apply any inference rule. Is there any inference rule that can be applied? If so, just try to do it. Right? So Lily, B, from conditional elimination, line 1 and 2. Good. Just as before, starting with just getting B. But now we have this goal, A and B. So we're not there yet until we get that on one of the lines. So we continue to the next, 4. What could be written on line 4? Sorry. Yes, but from what justification, Frida? That's correct. That's what I can write there, but I just need to know. Oh, okay. Well, actually, A and B would be a better way to go, I think. Because Frida, no, A does not follow from conditional elimination on 1 and 2. That's invalid, Frida. Let me explain that. From these two statements, B follows, not A, because it's the consequent that is derived from the two parts combined above. The full conditional and the antecedent leads us to the consequent. But this is not valid, okay? Like, so for example, if we have this, that is not valid. You cannot affirm the consequent and derive the antecedent. So it's from left to right, not from right to left. Okay, but anyway, yeah. Line 4, I see, Lily, you've given A and B. Good, and that is from conjunction introduction on lines 2 and 3. Now, Leonard, your question, could it be conjunction elimination? No, you wouldn't need to do that here because there was no conjunction above. You can't eliminate when there's no conjunction to eliminate. But we can build this conjunction from these two parts right there, A and B. Okay, so what I'm showing you here is how to like combine the use of multiple different inference rules to get to a single derivation result. A then B, and then A gives us B by conditional elimination on 1 and 2. And then, since A is already an available assumption, we can simply put those two pieces together to get the result we want right there. Okay. Conditional elimination. Now, one more inference rule to learn for today, and then we'll try some more practice problems from the book. This is a rule called reiteration. Reiteration. And the symbol for that is just R. And you see it here. So reiteration is kind of like, I mean, it's the most simple, in a way, rule of all of inference rules. All it says is that you can repeat something that was on a previous line later. So for example, from statement P, it follows that P. It's not exactly the most interesting of the rules, but it's actually quite useful later as we get to more complex proofs in the weeks to come. This rule will come back into play because it's needed when we get to what are called sub-derivations. Sometimes you have to be able to reiterate a sentence into the scope of a subderivation in order to close that subderivation. That's something, though, that we will talk more about next week. But anyway, for now, think about this. Okay, so suppose that the problem just says A. And you have to derive A and A. Okay, what can I do? How do I get to A and A from the statement that A? So, second step of the proof, where to go from there? Okay, reiterate A. So A, reiteration from line 1. With reiteration, there's only one line that is cited. With conditional elimination, there are two lines that are cited. The line where the conditional was and the line where the antecedent that matches it is. In conjunction introduction, there were two lines cited, the two pieces that you combine. And with conjunction elimination, there's one line cited. So you're one step ahead of us, I guess, Lily, and you're saying A and A on line 3. And that is correct. And it's for conjunction introduction, lines 1 and 2. Okay? So like from any fact, that fact, of course, follows. I mean, this is like a weird thing to say, but like I was born in March, and therefore it follows that I was born in March. You know, so like any fact can be reiterated. If something's true, it follows that the same thing is true. So from A follows. And then now that we have A appearing on two separate lines, we can combine them into one conjunction as required by the direction of the proof. Okay? Now, there's more derivation rules to learn. We're going to learn more next week. But I want to just like not overwhelm with too many rules all at once. We'll just start with these 4. And really, the reiteration rule is not going to be used just yet. So more or less, we're just having 3. Let's go down to some of the problems that you find in section 5.1 here. Okay? And I'll try not to spoil the fun. Let's try this first one here, 5.1.1. Okay, so this is problem set 5.1.1, letter A. And it tells you to do this. Derive A and B from the assumptions that you see here. So I'm pointing us to this part here on the bottom. I'm not scrolling up because it shows some of the solution, and I want us to think more about it before I show it. So here's the problem then. 2 assumptions provided, A, and if A, then B. And the problem says to derive the proposition that A and B. All right. So what's the third step of this proof? We're trying to get to A and B. And this is what you got to work with and the inference rules that we have learned. So what's the next step? The inference to make on the third line. You know, because you only have really a couple rules here. You've got conditional elimination, you've got conjunction and intro and elimination. Leonard, okay, B, from conditional elimination, 2 and 1. Good. I say 1, 2, 2, 1, it's fine to have it in either order. So this B results from eliminating this conditional. It says if A, then B. We also have the statement A. So anytime these two things exist, a conditional and the left side of it, we can obtain the right side by a use of the inference rule, conditional elimination. So we've got B. How do we get to the proof then A and B? There's still one more step. So what's the fourth and final step of this one? The fourth and final step of this proof. We need A and B. We have 3 sentences written. Okay, so A and B, conjunction introduction 1 and comma 3. Good. It looks like 13 at first, but I can see what you meant. There you go. That's the solution to this problem. And they didn't write the justification in the justification column, so they were trying to like kind of baby you a little bit, like, okay, here's what the steps would be. What would the justifications be that got you to those steps? Here in the solutions manual, no, not that. Wrong one. Yes, and so, oops, that's the instructor's one, the student's one. Yeah, so you see here, same. Moving this really fast so you can see everything. Derive A and B, here are the two assumptions. B follows from conditional elimination, 1 and 2. A and B follows from conjunction introduction, 1 and 3. And that's that proof. Okay, so we're gonna minimize this guy and this one and come back to the problem set, and let's look at number B. Okay, so here's B, and I'll write it up here on the board. Okay, so it says your goal is to derive this proposition, not the case that C, tilde C. And here are two assumptions given to get you started. The first is that if A, then both B and not C. And the second says that both A and B. Okay, so now it's all you. What's the next step? Any steps that can get us closer to tilde C, not C. So if you see an inference rule and it can be used, just toss it out there and let's do it. You know, anything that can be written on 3 that is a valid inference from steps 1 and 2 will get us closer to the proof. So, what do you think? Step 3. Step 3. What can be written for that? Okay, Leo, you're saying A can, well, let's get the correct rule though. A can be written, but not because of conditional elimination. And also conditional elimination would require 2 lines to be cited if that was the rule being used. What is the rule that you mean to speak of in writing down letter A? It's conjunction elimination of 2. Right. Let's make it clear, Leo, because line 2 is not a conditional. So there's no arrow here. So there's no arrow to eliminate. There is an and sign, and by means of conjunction elimination, we can strip off the left conjunct. Yes. Okay, no problem. Good. Just making sure we're all on the same page. So we're still trying to get close to this result in the end, not C. But whenever you add something to the proof, it's like video games, guys. Kind of it unlocks something. It's like it's going to unlock the next step towards the goal that you're trying to reach, right? So like you have a new item, which is the letter A now. Knowing about these rules and seeing all 3 of the previous available steps, it generates what you should do next. So like at each new line of a proof, you should be having these thoughts. What's available in all the previous lines, and what inference rules can I use now that I'm on this new step? Okay, so you're saying B and not C, both Nathaniel and Leonard, yes. But Nathaniel, although you're almost there, you just have to get the citation correct. The rule is conditional elimination, but how many lines must be cited? You have to cite 2 lines, the line with the original conditional, and then the line where the antecedent occurs. So you almost have it, but on line 4, it should be stated as it is there by Leo, B and not C. And the rule is called conditional elimination, but what are the lines 1 and 3? See that? 3 and 1. These 2 things give us this consequence. All right, so you just have to make sure to cite both numbers. We're almost there. We've got to just get to the tilde C. So what's the 5th step? It should be the last step. Now we're almost done. We just got to write one more line. Tilde C is our goal. What's line 5 going to say? Okay, Frida, tilde C, good. On the basis of conjunction elimination, line 4. And now that we've gotten there, we've derived it. So we're done, and that's the solution. Looking at the solutions manual. Sorry, here we go. And you'll see that here. Okay, so just as it's been written here. A, then B and not C, A and B, two assumptions. Okay, A comes from conjunction elimination, line 2. B and not C comes from conditional elimination, 1 and 3. Not C, finally, is the result of stripping off tilde C from this conjunction. And in 5 steps, we got to the solution. Okay, so there's more and more problems. And just get used to this. This is everything now. This is our whole class now. It's just endless proofs. It's endless derivations. Now, one thing that's kind of nice about that is that it eliminates all ambiguity. There's just like objective answers. You know, it's kind of like doing math. So if you're a person who's good with quantitative stuff like math, then this aspect of the course is very definitive, and there's just precise objective answers that must be arrived at in a certain rigorous way. Okay, so next let's look at this one. I guess for this one, for letter C, I might have to go into a different rule. So let me quickly check on the solutions manual to see which ones don't involve rules like that. Construction, introduction. Okay. And the other set of problems. Okay, we can do D. Let's do that. C will require a rule that I'm going to teach you next time. So let's do D. Okay, here's the problem. I'll write it down. Okay, so you have to eventually get to this result. Derive this big old conjunction which says that both E and D, both E and D, and also both not B and C. Okay, and in the proof there are 2 premises, 2 assumptions. The first and the second right here. The first one says that if not B, then both D and E. And then the second assumption given is that both A and not B, and C. All right, so it's going to take a couple steps, but we'll get there eventually to this result. For now, though, you have not too many options about what to do. So let's take some steps. What could be a third step? Given the limited number of rules that you're aware of, there's not too many things to choose. So what do you believe can be done on line 3? Yeah, let me know. I'm seeing the chat, and I'll just take it wherever you tell me to. Line 3. The third line of this proof. What rules do you know? You know conjunction introduction, conjunction elimination, conditional elimination, and then reiteration rule. Reiteration doesn't apply to this one, so you only have 3 possible ways to think about what rule can be used. Okay, you say, Leonard, A and B from conjunction elimination of line 2. Exactly, that's good. A and, and not B. Okay. Everybody, pay close attention. A and B is one of the 2 conjuncts in line 2. Line 2 is a conjunction, so it can be eliminated by conjunction elimination. When you use conjunction elimination, you can take apart any conjunction where its main connective is this. Since this is the main connective of the formula, we can remove the whole left side, giving us this new statement on line 3. But we're nowhere close yet to being done, so what's line 4? Okay, Frida, you suggest not B from conjunction elimination of line 3. Okay, good. That's good. I think of whatever. I'm like a puzzle master of Tetris, so maybe I speak in a way about this that resonates with me. But I think of if you think of it as like a game where you're just trying to get to the solution in the end, it can make it a little bit more easy for your brain to process. You don't have to get so mixed up thinking about the larger logical significance of all the issues being raised. You can just be like, well, there's rules, and there's inputs and outputs. What's going to be an input that will give me another output that I want? So good. You noticed, I think, Frida, that once this was made available on line 3, that gives us a new option to take it apart because it's a conjunction itself. Now we have not B, which is very good, but we're not all done. So what's the 5th step maybe? Okay, so Frida, you suggest removing the other conjunct here. Fair enough. So you said right to letter C, and that's from conjunction elimination of 2 also. All right. So we're making progress, but we still have some more to do. Next step, line 6. With the stuff that's available here and the inference rules that we've learned, there's a new move, a new inference that should come clear to you. What's the next move, you think? In row 4, you asked Marissa, can we also include line 1 in the justification column? No, because line 4 doesn't have anything to do with line 1. Line 4 is the result of stripping this away from line 3. It's not the result of doing anything to line 1. In line 1, not B occurs, but it's the antecedent. There's no rule that allows you to remove the antecedent from a conditional. So no, it's not at all involving line 1, no. Leonard, you say D and E from conditional elimination 1 and 4. Good. That we can do. Because if you look, line 1 is a conditional. This is an arrow symbol. That's the main connective of this sentence. Well, conditionals can be eliminated when you find the antecedent part. And that's what we do have in line 4. So now, let's combine 1 and 4 to get to the consequent there, D and E. D and E is conditional elimination line 1 and 4. Okay, so more steps have to be taken next. And let me see what I've got here in the chat. Frida, just remember, when you do conditional elimination, you have to cite 2 lines. So you're right, conditional elimination, but 1 comma 4, because that's where this part of it is. You see the tilde B that matches that? There's always the 2 lines cited in conditional elimination. Okay, Lily, so now you give tilde B and C by introducing 4 and 5. No problem. Okay, so tilde B and C, that's conjunction introduction, line 4 and 5. See, just 4 and 5 had just been smashed together. Now they say tilde B and C. Very good, because that's this component. So once we get E and D, we'll be able to just add line 7 to it, and then we'll be done. But we don't have E and D. What we do have is D and E. So on line 8, we need to do something to that. Tell me what to do on line 8. The order matters in terms of not like the logical meaning, but at least the syntax. We insist that you compile it in the required order. Okay, so Leo, you've taken E from number 6 by conjunction elimination. Good, because line 6 is a conjunction, and therefore it can be disassembled. So you've taken one part of it off, and then in another step, you've taken the other part off, have you not? Well, maybe you didn't say that yet. Oh yeah, you did. So D is also the result of doing conjunction elimination on line 6. 2 more steps. I know I'm running low space on the board, but we'll put them both down here. What's step 10 then? Step 10. Good, Lily. Step 10 is to rebuild this conjunction in the needed order, E and D. And we do that by taking the 2 components from 8 and 9 and recombining them. So that gives E and D, conjunction introduction 8, 9. So finally on the last step, line 11, what's the justification and what is the sentence and all of that? Line 11, the last line of this proof. Okay, E and D and B and tilde B and C. The right parenthesis on E and D should be in there, but I think that's just a typo from you, Frida. But you're correct. Well, actually, not 100% correct because of the numbers that you cite there. You cite number 6 and 10. 10 is one of the numbers to cite, yes. But what's the other one? Do you see it? Because look at what's to be derived up there. So that much is clear. E and D and not B and C. So like basically this formula is what's written in 11. The justification is, 7 and 10. So this is conjunction introduction 7 and 10. And there we have the solution. To see it in a little cleaner version, I'll put it here in our chat, or rather on the screen share. Sorry. So yeah, you see here. Well, actually, oops, that's the one with a blank. So let me put it up from not this one, but this guy. Okay, yeah. So yeah, here we go. Okay, so notice here's the problem. It says derive E and D and tilde B and C. Got these two assumptions, and it goes in the same order pretty much. Maybe some of the steps have gone in different order, but it's the same answer. A and not B is by eliminating line 2, and that's what we did here. Conjunction elimination. Not B is from conjunction elimination in line 3, and that's also what we did here. D and E, I guess they just chose to build that up next by doing conditional elimination, but we did it on the 6th step. That's fine. D coming from line 5, conjunction elimination. E coming from line 5, conjunction elimination. Then those two things recombined in forming E and D, conjunction introduction, on lines here, 6 and 7. Then the line number 9 is C, which is conjunction elimination of line 2. We did that a little earlier in the proof, but it doesn't matter when one does it as long as it appears there eventually. Line 10, conjunction introduction from 4, this statement, and 9, this statement, builds this. And then finally on line 11, we can build the whole formula up because we have the two conjuncts that are required. Line 10 here, and in our proof it was line 7, and theirs it is line 8. But it's 11 steps, and the same 11 steps. So just very kind of clear, precise writing of it there. All right. So let me just stop sharing that screen. And oops, here's the chat. Good. So today was our first kind of taste of doing derivations and learning how to do proofs in logic. My goal was to show you how to do conjunction introduction, conjunction elimination, and conditional elimination. And those are the 3 rules that were used in all the proofs that we attempted today. When we do return next week, we'll start learning the other derivation rules, which will give us the ability to do more sophisticated proofs. But that's all there is left. There's just more derivation rules to learn about, more proofs to conduct, and of course we want to hold on to all the information we learned earlier in the semester. But the current homework, homework 3, does not have any proofs in it. The 4th homework, the last one, is going to be all just proofs. So you know, I'll assign that 4th homework to you after the 3rd one is due. And then the final exam is going to have a mixture of all concepts in the class, but proofs will be an important component of it. Maybe 30 or 40% of the final will be about proofs. Okay, so any questions for now? If so, let me know. If not, I'll let you guys go and catch up with you, I guess, later on. I'll be finished with all grading from the midterm this weekend, and I'll let you guys know as soon as it's ready, and you can check on your score for that or for anything else. Otherwise, I guess we're all good, huh? Are you guys ready to roll? Are we on the same page? Just let me know in the chat if you can hear me loud and clear. Okay, thanks, guys. I'm going to close this stream, then I'm going to close the YouTube stream as usual. So take care, have a great weekend, and be in touch if there's anything that you need from me. Okay, bye-bye. And okay, to my YouTube people, hey there, I'm closing this one now too. Make sure to come back to this at any future time if you would like to review some of the notes that we discussed or any topics. But have a great day, and I'll see you next time.